is, don't worry about that. I'll get to that. And we've already seen kind of a quick definition for what the ICD-10 codes are. But for the overview of this talk, I actually want to start a little bit higher level and thinking about how do we come at the problem of integrating LLMs into our workflows. And that's mostly because there's so much hype around LLMs. We see like these nice examples of things that they can do. We're not always sure what they can do consistently, and it's not always clear how they should be integrated into biomedicine problems. And because in biomedicine, our problems are a little bit different, right? So if you talk to like a lot of tech people, they're a lot of times they're thinking about how to sell ads. Now, biomedical applications are very different because the objects under study for us are humans and human health. So we really need to be a little bit more careful about how we integrate new tools, and then how we think about making sure that the tools are doing the things that they're supposed to be doing. So I'm going to start with that. And then after that, I'll go over just a quick ICD refresher. I'll tell you basically what these embeddings are and how they work. I'll show how we validated them. In other words, how we made sure that they actually do the thing that they're supposed to do. And then I will go over a little bit of use and reuse. For this paper, we spent a lot of time making sure that other people could use the products, or the data products that were produced. And I'm just going to show how to do that. And I think that was actually one of the things I was the most excited by, is not only did we get a paper out for this, but we have kind of a set of, or we release data sets that are supposed to be, maximally easy to integrate into your own analyses. So I'm going to actually start at So I transitioned off of Yale. I was the director of the data science pathway, and I was teaching data science software systems. And then I finished up with a capstone course for the biostat students in the data science pathway. So on the last day, I showed them this graph, and I explained this is basically from a pancreatic cancer study that we had permission to release. And I showed the students this graph, and I said, what does this graph show you? All right. And it was meant to be kind of open-ended, but I wanted to get some participation and see what the students would say. And this particular class was relatively quiet, and I got almost no responses, right? So this is a pretty basic Kaplan-Meier curve. I just wanted to see, can you provide some interpretation for this? These are students that are about to graduate. They should be looking at this and saying, oh, well, this is, so this is going to be overall survival, or this is progression-free survival. So I know that's the end point. What's happening? It looks like we have about, we have 2 therapies that we're evaluating. It doesn't really look like one's doing that much better than the other. And so I was looking for just some kind of response for them to, and I didn't really get anything. So what I did then was I took this visualization and I actually dumped it into ChatGPT, and I said, can you provide an explanation for this? All right, and so this is the actual response that this is ChatGPT 4.0, so this is pretty recent. So it says the PFS plot shows no significant difference between the first therapy and the second in pancreatic cancer patients. Both treatments have similar progression-free survival rates with a median PFS around 3 to 4 months. The overlapping curves indicate comparable efficacy, suggesting that adding the 2 therapies does not improve outcomes compared to one alone. Both treatments show limited effectiveness in delaying disease progression, highlighting the need for better therapeutic options. So I had done this before actually going into the class. The thing I like about this is this is actually a pretty nice summary of the visualization. And if you want, you can always go back and verify it. So just to get, because I was a little bit annoyed that the students weren't more participatory, I asked them, I said, if I have this, why do I need you? And I had said that, again, just to be a little bit, not cantankerous, but to try to get engagement, because I think there is this attitude now of there's uncertainty in terms of what are LLMs going to accomplish, and what does that mean for us, right? And I had posed it in this way that is a little more adversarial, because I do see a lot of the students thinking like, this is that this is something that's potentially going to take their job, right? This is going to be something that limits their opportunity for career and then also career advancement. But so after I let them kind of stew on that for a little bit, I told them that your attitude with these new technologies should be that this is great, right? Not that this is something that's going to take something away from you, but this is going to change and make your job better, right? So I want to point out that LLM automation means implementing and interpreting analyses just got easier, right? I think one of the problems or one of the challenges, at least for me as a data scientist, is I really like building software infrastructure. I like doing analyses, and I like working with clinicians. And those are actually three pretty distinct activities. And for me to context switch between those actually takes a lot of effort. And sometimes I don't context switch very well. So anything that's going to help augment my capability with any of those three areas is going to be very helpful. So basically, we have this new resource to augment our programming, analysis, and scientific knowledge. Like I said, I tend to work with clinicians. I don't usually know quite as much about the science that I'm trying to build hypotheses for. So this is now a resource for me to be able to query and gain scientific knowledge as it's relevant to an analysis. It also means that if I'm spending less time on these things, I can be thinking about what is the thing that I can build upon, given that I have these new capabilities, right? It's not that I'm not stuck with doing the same job. If I can automate part of my job, then I can think about how do I elevate myself based on those capabilities that are now available. So what I think we should really be thinking about is that our role is probably changing so that it is elevated, and it's really about conducting the generation of information, verifying its validity, because we know LLMs they're not always accurate, and we need to be able to provide validity, and then also we need to evaluate relevance. So there's this observation that we almost get to do a little bit more management than we had before. And then I just want to close this point with there's this old quote. It's from a 1979 IBM presentation that says, a computer can never be held accountable. Therefore, a computer must never make a management decision, right? So we should be thinking of our role, I think, a little bit more in terms of the management of information and how and what is provided to the people that we're working with. Because a computer is not going to be able to make those types of management decisions because it doesn't have the context, and it's probably, at least for a while, not going to be fully aware of the context and the goals of a project. All right. So at this point, I've been working in technology. So my background is actually in computer engineering and then electrical engineering, and then my PhD is in statistics. I'm a little bit late to biostatistics. So I think I came to biostatistics with a little more of the attitude of a technologist, and I have a lot of experience basically integrating new technology and figuring out how to integrate new technology. So as kind of the guiding principles that I use is that I don't try to compete with technology, right? If my job is squarely something that's going to be automated, then I need to think about how to change my job to be able to use that technology. The other thing is, we see this right now, is that we should always be very skeptical of the marketing claims that we see. I think we might be coming off peak AI hype. Maybe there'll be new hype coming soon, but we should be skeptical that these new technologies are going to be a panacea. A lot of times they're very useful tools, but they're not well contextualized, and their usefulness isn't well contextualized. So a lot of our job is figuring out how is it useful and how can we use it to our advantage. I am pretty aggressive about understanding and integrating new technology, just being aware of what's available now, what are people worried about. but then pretty conservative when thinking about how to integrate it. And again, that's because, that's partially because that is pretty critical in bioscience. In bioscience, because we're dealing with people's health, when we basically need to have more accountability for predictions that we make. We also have these distinguishments that if we're making decisions in biomedicine, a lot of times we need to think about our uncertainty in our estimates and think about how does that actually go into a decision process? What are the risks that are involved? And then how much risk is there? Now, that's kind of for technology in general. If we want to be a little more specific for LLMs, I think one of the most interesting problems right now is validating the results of LLMs. Basically, if we're using an LLM to try to generate information, how do we verify that information? The way that we do it right now is that we actually look at the results. We say, does this make sense? Does this correspond to my intuition? If it doesn't, why doesn't it? And what is the knowledge that I can actually gain from that? My current work is a little more focused on what are alternative methods of validation, particularly in RAG systems. How do we make sure that the results we're getting back are correct? LLMs. So another thing to realize is they're not programmers, software engineers, or data scientists. LLMs can generate code. I think I'm still pretty skeptical for the program generation. I think if you look at the code that LLMs generate, they can generate decent code for the successes have been for pretty specific contexts, right? So it can generate a Shiny app that's not too different than the template Old Faithful example that comes up when you say, make me a Shiny app in our studio. It doesn't usually understand kind of the overall goal of an analysis. Again, unless that goal is pretty short term or pretty small, and it's not necessarily going to be great at putting those things together like a data scientist would. So, I think it's probably going to be a useful tool for things like Copilot or something like that, but it is a little bit limited in terms of what it can do. I guess going towards that, I think that is also an interesting problem. And the reason it's interesting to me is that you can ask an LLM usually for a simple example to generate code, and it's going to do a really good job. Once again that task becomes more sophisticated, its performance is going to degrade. And I think one of the things that is the most interesting for me is that when we design large-scale software systems, a lot of times we have this idea of a specification, right? And if I'm just typing something into an LLM, it's kind of giving me an average solution to my question. For a large system, you're usually building something new, so you rely more and more on a spec. So my speculation with this is that we're going to see more emphasis for when LLMs are coding on how do we provide a well-posed spec, and then how do we create tests to make sure that if we're going to use an LLM to write code, that we can actually verify that the code does the thing that it's supposed to. So I guess to bring this back down to the meat of this talk, what we were really interested in for these ICD-10 codes is how do we integrate LLM embeddings into our analyses. So the problem that we were running, or that we have, is that we're dealing with there was a clinical trial called STRIDE, and we were essentially trying to match the relationship between ICD-10 codes, which again tell you about all these disease and diagnoses, and we were trying to match those with insurance claims to say whether or not it was a match. So for these ICD-10 codes, as was mentioned before, this is the International Classification of Disease. This was put out by the WHO. We're using the clinical modification for these. And they're used in health records for several reasons. So clinicians tend to be really into categorizing things, but once you have those categories, you have a consistent set of diagnoses that are going to be standardized. We can use these then for data analysis and research, rather than having a description of of a disease, we now have a specific code corresponding to what the disease is that's going to be consistent across, within a hospital, across hospitals, and so on. We can use those for quality management and improvement. They do get used for reimbursement and billing, and then also health policy. Just a small note, the ICD-10 codes do change per year. They are meant to be, for a given disease, they are meant to be consistent across years. But basically, as diseases are subcategorized, the set of ICD-10 codes does increase, albeit slowly. All right, so like I said, I am going to show a little bit of code, and and I'm going to make use of this repository that we put up to accompany the paper. So this is so my handle on GitHub is Kane++. I used to program a lot in C++. So that's my handle. And then this repository, it is public, and it's called ICD-10 CM Embedding. All of the artifacts and analyses that I'm going to show here are reproducible from this repository. And if people end up having questions about it, I'm happy to answer. So what do these look like? So again, so we have a copy of the ICD-10 codes in the repository. This first set of code is, I'm just going to grab this. So this is the URL on GitHub to grab the ICD-10 codes. I'm just going to write this to a temporary file, read it back in. We did make sure when we downloaded that code that the representation of the ICD-10 codes is exactly as they were downloaded. That's in fixed width format, which is a little bit dated at this point, but we did include the code for actually reading that in. If you read that in, then you see what you have is, I'm going to have a data frame or a tibble with two columns. The first column is the code, so that actually is the ICD-10 code, and the second column is the description, so that's what is the corresponding disease or diagnosis. All right. So just as a little bit more background on the ICD-10 codes, what do they mean? So the first letter represents a category of disease. So as an example, J represents respiratory conditions. The second and third numbers that further specify the disease category. So for example, J45, so J is respiratory, 45 actually corresponds to asthma. So so it is a little bit hierarchical, and you can also see from the first couple as an exemplar that when these are close, the descriptions are usually pretty close. They don't have to be, but they can be. And then there's the remaining characters basically provide additional information about the condition, right? Okay, so what are the challenges of integrating ICD-10 codes into an analysis? So this is essentially a categorical variable with 72,750 levels, right? So if I were thinking about incorporating this as a variable in, let's say it's in a supervised model where one ICD-10 code is one of the independent variables, then I'm going to need to do a factor expansion on that, right? So basically a dummy encoding. And if I have to do that over 72,750 variables, I'm going to end up with a matrix that is 72,750 columns just for that one variable. All right, so that's a huge problem. Mostly because even though it was one variable, you now have a high dimensional problem. That means that you need to be careful. So I would start worrying about, do I have enough data to actually learn over those variables? And then how well is my model going to learn the relationships between those dummy encoded variables, which have little to no information with my dependent variable? So it can be made a little bit simple. People have kind of done in the past, right? So if you look in paper for what people have done is they'll use the first three characters. So in that case, you're talking about so because we're talking about a letter and then two two numbers, you're talking about a little over 2,000 variables. So we've decreased it by about an order of magnitude, which is pretty good. And then maybe for a lot of the studies, what people do also is they'll say, well, I don't need all of the ICD-10 codes. Let me just look at this specific set of patients and incidences with specific ICD-10 codes. Then another thing people will do is a lot of times with these supervised problems, you will see that when you're dealing with EHRs, you're not usually dealing with one ICD-10 code, as you could have some number of ICD-10 codes. And a lot of times per sample, the number of ICD-10 codes you have can change. So maybe people will add up the dummy variables and try to use that. Again, it's still high dimensional. It's still a difficult problem to work with. So we end up worrying about, do we have enough data or enough samples to actually learn these categorical relationships? All right, so I want to make just a couple of observations that'll kind of get us to the next part. And that's, again, the categories themselves are informative. So we know that both the coding is informative in terms of the first letter. We know that we have these descriptions that actually say what is the disease or diagnosis. So we're throwing out a lot of information if all we're doing is the dummy encoding. A category is related to other categories. So, we saw before the first couple of categories were related to cholera. So one cholera category is going to be kind of closer in some semantic sense to another cholera category than others. So, again, thinking about the dummy encoding, we're kind of throwing out that information. So what we'd like to do is use those semantic relationships to create informative features, not just dummy encoded relationships that we have to learn. So then the motivation for this paper was, can we use an LLM to encode those relationships among all the categories? Instead of doing a dummy encoding, can we come up with a representation for one ICD-10 code? If it's close to another, that actually means that those diagnoses are close. All right, so the way we did this is with an LLM embedding. So just as a review, this is kind of a simplified version of how we were thinking about the LLM. So basically, you have this input text for the ICD-10 codes. It's going to be the description. What was the diagnosis? That is going to be tokenized, which means that it's going to go from from the set of words, the input text, to a numerical representation to represent the sequence of words. It's going to go into a text model. And from that, we're going to get an embedding. So the embedding is a vector representation of the data after it's gone through the text model. So if you're generating outcomes, then what happens is there's usually a perturbation on the embedding, which is a parameter that's called the temperature usually, and then it's decoded into output text. All right. So the idea is, after coming out of the text model, we get the LLM embedding, and this is providing a semantic encoding of the input text with relation to with the other input text. All right. So then the idea is similar input texts are encoded closer in the embedding compared to those that are dissimilar. The similarity is kind of so actually quantifying that similarity is a little bit difficult, right? Because we're starting with words. And we have to say, well, how close are two diagnoses? So, for example, is a broken arm more similar to the flu or cancer, right? Which I don't really know. So there's this weirdness to think about for that the model encodes, that it's coming up with these relationships based on the semantic similarity, and that's all based on the input text that it was, that's based on the model, and the model comes from the text that was used to train it, right? So what happened, especially early on, is that the LLMs, I think, were a little bit more context specific, or could be made more context specific. I think one of the interesting things to see now, especially with the larger LLMs, is how fast they can context switch. But this work is about a year and a half old, and at the time the LLMs were smaller, and we were seeing a little bit more specialization, right? So the LLM model that we decided to use was BioGPT. So this is an open source model that was developed by Microsoft, tailored specifically for biomedical research and applications. So it was fine-tuned on PubMed abstracts. So after doing the initial training for understanding at the time, that training was basically, you would take, for example, a paragraph, and you would give the first sentence, for example, as input, and it would try to estimate the next sentence. So that was the training process. That has changed, especially with companies like OpenAI, where they're now geared a lot more towards question and answer. But at the time, kind of for the original models, it was input text, estimate the output text. And this BioGPT was originally trained for kind of a general set, and then it was fed the PubMed abstracts, which kind of helped to specialize it towards biomedical applications. So this is a relatively small large language model, so it's only 350 million parameters, which still seems like a lot to me. It is open source, and it's relatively easy to use. And by easy to use, I mean that it does run on my laptop, right? All right, so I just want to show, I'm going to include code. If you actually want to run BioGPT, it's actually pretty easy to do. This is an example using Hugging Face, and this is from R using the Reticulate library. So so my examples are going to be in R. I'm a little biased towards R compared to Python, but and part of that is basically all of the utilities that you may use or need or want in Python are kind of available to you from R through Reticulate. So included in the repository is a script for creating a conda environment. It's called BioGPT, and it'll actually load the BioGPT model for you, and then also the associated libraries. So if I want to actually play with BioGPT and say, what kind of text does it generate? I basically have an example here that's going to do the tokenization and then create the model, and it can actually output for you. So in this example, you can think of this as boilerplate code to set up those different LLM components. And I'm just going to start. I'm going to create this generator, which is basically I'm saying complete the sentence, and it's complete the sentence. Patient came in with. All right, so it's already tailored towards biomedical applications. I'm going to give it this text and say patient came in with, and I want it to complete this for me. So so it's going to complete it with a patient came in with 2-month history of fever and left a bunch of medical words. This is probably kind of an average of what it was seeing from again from those PubMed abstracts. So if you want to download this and play with it and see what BioGPT can do, you're more than welcome to do it. It's not going to be nearly as impressive as ChatGPT. At the time, it was pretty impressive. It's not particularly good at question and answer. It's really geared more towards, again, how do I complete the sentence from a medical corpus? All right, so if I actually want to get the embedding, I'm not showing some of the code here. It's again available in the GitHub repository. But what I want to do is just make sure that intuitively, I believe the results for the embedding. So again, the embedding is this numerical representation of a term or sentence. And so what I'm going to do is I'm going to pick a couple of conditions. So here I have appendicitis, surgery, broken arm, broken leg, asthma, wheezing, and heart attack. And I'm going to embed these strings using BioGPT, so the result will be this variable called EEVS. I forget why I called it that. Maybe that's not the best name. But if I say then, what are the dimensions of this? It's going to be 7 by 42,384. So I have 7 terms in this EVS, and the embedding dimension, so the number of dimensions in which I'm putting the text, is 42,384. If I look at the distances, so each row corresponds to one of these terms. If I just look at the distance matrix of these terms with respect to each other, I can see the results are pretty encouraging, right? So broken arm and broken leg, those are both breaks on limbs. And so maybe not, or hopefully not surprisingly, in terms of the embedding distance, so this is just the L2 distance, they're very close compared to any of the other conditions. So during class, we kind of went through and, what are other terms? How close are they? If you want to go back and see, is broken arm closer to appendicitis or cancer, you can go and do that. And the code is relatively simple. So what do the values actually look like? So if I look at the first row, which corresponds to, again, appendicitis, these are the actual values. I'm only going to show the first 10 values, but this is a vector with 42,384 elements. So we've already accomplished a little bit, right? We have we've gone from about 72,000 dummy encoded representation of 72,000 down to 42,000, where we've shown that there are some semantic relationships that are being preserved, but maybe we want to do a little bit better than that. All right. So the next thing we're going to do is essentially a dimension reduction via autoregression. So rather than 42,384, that's still a lot. It's still a really high dimensional problem. We're going to use an autoencoder to reduce the dimension further, right? So at this point, we used an LLM, and I felt like we were all in on deep learners for this project. So of course, we're going to use an autoencoder. If you want to, you can look at the you could do principal components. That actually works pretty well. We just chose an autoencoder in this case. So what we're going to do is an autoencoder for a couple of different dimension reductions. And then we're going to think about how do we actually validate this? All right, so just as a reminder, for an autoencoder, you have an input. So these are going to be, in our case, this is going to be the embedding values. All right. And then it's a series of fully connected layers that get smaller and smaller. So in our case, the first one is 42,384. We're going to reduce it. I was reducing it by about an order of magnitude. I think the autoencoder we used had 2 layers, and then it gets reduced and reduced down to this lower dimensional representation. So from that, we're going to go back up to 42,000, dimension 42,000. And the way this is trained is that I want the vector value going in to be the same as the vector value coming out, right? So what's happening is I'm iteratively compressing the data and I'm optimizing the network such that it's going to retain as much of the useful information as possible, so that this representation, this lower representation, retains the information. And I'm basically training the autoencoder such that after all this, I can show that it's retaining the information by looking at the difference between the output and the input, right? So I want to minimize that. All right. So if we do that, here are the results. So for the deep learners, there's always a couple more parameters than you think there are going to be. So we basically did, we built a bunch of models and then said, and did a shootout for them. So we were looking at different embedding dimensions. So we did 50, 100, and 1,000. We did play around with the batch size. That means for each one, so a batch is going to be a subset of the data that I'm using to calculate the gradient to try to optimize the network on. I never really know what that's supposed to be, so we tried a couple of different combinations. The validation loss is how much am I losing? So this is just the mean squared error between the output and the input, and then the training loss, which we expect is going to be a little bit lower, just because that's based on the data that we're building. So what this is showing is that, let's see, let me just sort this in the embedding dimension. What this is showing is that our validation loss, there's some variation, but in general, what we're seeing is that as the embedding dimension goes up, in other words, as I have more dimensions here, my validation loss goes down. right? So basically, the less I have to compress the data, the more information I'm going to retain. Okay. Now these are an absolute. They're not. It's not really great for kind of saying, well, how good is that? So, but I guess if we go back, we say validation loss. We said it was a mean squared error, 0.6. If I go back to the actual embedding values, you can see they were usually, between -10 and 10. They get a little bit smaller, they get a little bit bigger, but we're in the second order of magnitude here. And this is on a vector that's, again, starting out that has length about 42,000. All right, so it looks like it's doing a pretty good job. The other thing that we were a little bit worried about was basically how much variation do you actually see over a year, right? Because we know that we know that the ICD-10 codes change over a year, and we wanted to make sure that it wasn't changing so much that we needed to make an autoencoder for each year. So what we did was we trained on 2019, and then we said, well, what happens if we reuse the same autoencoder, no training, on the different years? We're going to take the best of the models for each of the embedding dimensions. And so what we see is that the prediction error is actually pretty consistent across the different years, right? So you can see in 2019, so I'm going to refer to this. So this is the coefficient of determination. So basically, how much variation is there in the vector to begin with? So how much prediction error is there, and basically how much are we able to compress the data and maintain? How much are we able to compress the data? All right. So when the coefficient of determination is smaller, it means we're doing a better job of. It means we're retaining more information, and when it's bigger, it means that we're not. So for example, it means, let's see. So then for 2019, for embedding dimension 1000, our coefficient of determination, the variation that we're seeing is that we're able to capture with 6% of the information in the matrix or in the vectors. We're able to maintain a pretty low prediction rate, right? So the bottom line with this is that we're able to do this compression. We can see that the validation loss is relatively small in what we expect for in the embedding values. So what it tells me is basically that the information in the ICD-10 codes it's encoded, or it's written in those 72,000 dimensions. But what we can do, but the information is actually on a much lower dimensional subspace. So we're saying we can compress it and then decompress it pretty well, but we still haven't really validated it, right? And the thing that we were worried at this point is that, that in the original representation for the vectors, we showed that semantically, if two things are close, they're going to be close in the embedding. It wasn't clear to me that translates to the dimension reduced version, right? So just because I have a good compression doesn't mean I'm maintaining all the relationships that were in the original data. So what we really needed to do then is think about, how do we validate this? How do we say, if I want to use this lower dimensional representation, that it's actually going to maintain those semantic relationships within the data? So the way that we did this was so usually to do validation, you really need an independent source of data to show that the embeddings can be mapped into their original categories. So far, all we had done is embedded the descriptions, right? We hadn't actually used the ICD-10 codes themselves, which we know are actually informative. So to validate, what we're going to do is say, we're just going to see if I take the embeddings can I learn the categories from that? So I'm going to create a supervised model that's going to try to estimate the category based on the feature vectors, and these are the compressed feature vectors. If I can, then that's telling me that those relationships, that some aspect of those relationships are being preserved. I guess another thing you could do is say, are you maintaining pairwise relationships? But that ends up being a pretty big calculation. And what we really want to do is we don't need maximal accuracy. Like we're not going to be disappointed if the accuracy is 70 or so percent. We really just want to make sure that that we're maintaining some aspect of those relationships. Yeah, so we're going to use this as our validation, and the idea is again that it is a separate source of information that we can use to verify not only are we doing a good job of compressing, but we're maintaining these relationships that we care about for analysis. Right. So if we do that, these are the results. So again, we took the best of the models for each of the dimensions based on, so that's over the batch sizes. And here we have the accuracy. So, accuracy is about 80%. I did report the balanced accuracy here. And the reason is that this is not a binary classification problem, right? So there are 22 different categories, different letter groups, basically. So, chance is going to be something closer to 1/22. The number of ICD-10 codes in each category varies, but roughly, that's what we would be thinking by chance. So the thing to realize is we're actually doing a pretty good job, right? I said I was going into it. We said we were going to be happy with something around 70 to 75%. Our accuracy starts at 80, or balanced accuracy starts at about 70. And what's happening is that as you increase the embedding dimension, your balance accuracy is increasing, which is again saying that the higher the embedding dimension, the more predictive information you're allowing to go through the autoencoder, and that's being preserved in that low dimensional representation, right? So that was encouraging. The next thing we wanted to do is say, well, what if we compare against the current some of the other current language models? So again, at the time we did this, I think I did not have a subscription to ChatGPT, and I think we were at about ChatGPT 3, maybe 2.5, so it was pretty early. So what we did was we compared against some of the other open source models. So this would be like Clinical BERT, PubMed BERT, and so these are kind of similar models, but kind of previous generation. And what we're seeing is that the embedding dimension for these was actually, it was a little bit higher than our average. So there, it's using a little more data. The accuracy isn't nearly as good though. So so for balanced accuracy, if you don't mind going to 1,000 dimensions, and you want to estimate the category, we're at almost 93%. Whereas for these other models that are again available, estimating these these 22 categories, you're really a lot closer to something like 60%. So even in our lowest dimensional case, so that would be a 10-dimensional representation of the ICD-10 codes, we're still a little bit above what was the state of the art, which was Clinical BERT at the time. Right. All right. So at this point, we were pretty confident in the results. We thought this was probably going to be something that's pretty useful. So I just wanted to go kind of quickly over how to actually use it. So one of the issues, or one of the things I did not like about with the other models, is to use these guys, I had to download those. And again, because of Hugging Face, this is an order of magnitude easier than it was 2 or 3 years ago. But I still had to download the model, make sure my Python environment was correct, make sure I had the ICD-10 codes to put through it, put through the ICD-10 codes, and then perform the evaluation, right? But we can do a little bit better, because if we fix on ICD-10 codes, then we're really just talking about a lookup, right? What I want to do is, if I'm going to use this in my analysis, I don't need this model. All I need to know is what is the embedding for the ICD-10 code. So all of those are available on the GitHub page. So as an example, if you want to see how to do this, I'm going to download a couple. So I'm going to do a really pretty simple example where I'm going to download one of the embeddings. I'm going to do, and then I'm going to run tsne on it and then visualize by the category. So to do that, I'm just going to download this first file that is again available on the GitHub page, and all it is it's an RDS file, which is the binary representation for R. In this case, it's a data frame. I think we have the CSV files up there if you're more of a Python person. So you can download that. And all that's going to do is give you the which year we have the embeddings for, what is the embedding dimension. So again, the smaller the embedding dimension, the less the smaller the data set that you're going to download, and then the URL for it. So this will grab that for you. If you actually want to grab one of the data sets, basically all you have to do is say, give me the URL, which is again this third column, where in this case I'm getting for the year 2019, where the embedding dimension is 50. All right. After that, I'm going to grab a subset of the categories. The reason for that is this is just meant to be kind of a quick example, where I might be interested in a subset of the categories. I'm going to grab those. I'm going to fit a tsne to it, and then I'm going to do a visualization for it, right? So here's the code. Here's the results. I did do the transformation between the category code and the actual system. So G is nervous system. So it's nervous, circulatory, respiratory, and digestive. And this is the representation of the ICD-10 codes for these categories using tsne. And again, I'm not really married to tsne. This isn't meant to be like an analysis where we're gonna some deep scientific knowledge. It's a little bit more of a sanity check to make sure that that it's working the way that we think it should. So what this is telling us is that there are a lot of these circulatory, especially down here, there are a lot of these circulatory diagnoses that are very different than the others. Where you get a lot of overlap is where you start to see where the codes are more similar. The other thing to note is, again, this is still a high dimensional data set. So even though these are close, you may be able to distinguish them pretty well. We already know from the results before that if you use 1,000 dimensions, you're going to get about 92% accuracy for all of the categories. So even though they may be close in the tsne space, we can do a pretty good job of distinguishing them. All right. So if you want to use it in your analysis, the way that we kind of intended for this is that if you download one of these things, this is actually the 50-dimensional representation. You get a data frame. The first column is code, the second column is description, and then after that is the actual the vector embedding values. So this would be a straight substitution. If you're thinking about how to do this in an analysis, I would go through and say, if the code is one of my x's, rather than having the code, I would put in this vector, and then perform whatever analysis it is that I want to do. All right. So if you want to rerun the analyses, this was made to be so simple that even I could do it. There's a script to set up the conda environment. That's make BioGPT conda environment. So in Python, or sorry, I did this stuff from the shell. This will actually install the BioGPT environment for you, including the model. And then what you would do is sequentially just run 0 through 4, and it would do it would perform each one of the steps. All right. So I guess as a summary, so the thing we're able to show is that the LLM embeddings are an effective alternative to dummy variable encodings. So they're going to retain these semantic relationships. The relationships will likely outperform more traditional dummy variable encodings, especially for these supervised problems. The embeddings do retain more probably predictive information when compared to when compared to the legacy text models, and then also the dimension reduced embeddings. You can basically trade off the size or the dimensionality for this relational accuracy between the different categories. Just as a kind of just one last note, one thing we are interested in right now is, again, we run into these cases a lot where for any one of our samples, we can have one or more ICD-10 codes. One of the things I really want to try with this is if I just add up the embedding representation for the corresponding ICD-10 codes, can I handle that case where the number of ICD-10 codes changes per patient, and just by adding them up, I can reduce. I can have a representation that includes all of the ICD-10 code information without actually needing to go wider in terms of the number of independent variables, and that's something we're looking at right now. All right. So that's a talk. Thanks very much for listening, and I'm happy to answer any questions that people have.
Thank you very much, Dr. Kane. This was awesome. And I have actually done a project using your CSV files, so I can attest to the fact that they are really easy to use. And in my project, I did add up ICD code, like embeddings for a patient to create patient level embeddings, and that worked very well too. So this was really awesome. We have time for maybe one or two questions, quick questions. Sounds like it was all completely clear to everybody.
Right, great. I'm happy to hear that.
Thank you very much. This really was amazing, and this was a great talk. I'm sure there will be other people who will be interested also in listening to it afterwards. And if more questions come up, so next week we do have an informal Gen AI club session next Thursday at 3:30, where we can potentially, like digest some of the things that you shared today and discuss further so that we can understand better in a hands-on manner, and maybe more questions will come up then, and maybe we can reach out to you at that point, Dr. Kane. Okay, great. Thank you very much. Yeah, thank you again for your time. Yeah, Mike, you have something to say? Okay, thank you very much, and have a wonderful evening, everybody. Thanks.
Thanks very much.
Thank you.
Bye.